All right, so let's get started. So one thing that's left over from the end of Tuesday's class, somebody pointed out the fact that one of the, for gradient descent, one of the trials did much, much better than any of the other trials, right? They were all going along together, and then one of them took a nosedive and wound up having much, much better error. So this is kind of a subject of current research. It turns out that there are some recent results where if you have a really well-behaved problem, so for a statistical problem, well-behaved means that you have essentially a pretty good signal-to-noise ratio. You don't have predictors that are too highly correlated, right? So if you have one feature that is almost perfectly correlated with the other feature, then you can't tell what the weight is going to be, what the relative amount of weight is going to be without a lot of data. You can have more predictors than observations, but within reason. And in problems like this, you can sometimes get much, much better than the 1 over k convergence rate that we proved for k iterations. And so, for example, the paper that's cited at the bottom of the slide here shows that for some of these, quote, well-behaved problems, you get an error bound that looks like this. So here, right, is where you would ordinarily get a term that was something like 1 over k times the distance between the initial and the optimum point. Here you have c to the k, where c is a constant that's less than 1. And so this is going down exponentially fast, which is kind of cool. Or linearly, if you're one of these pessimistic numerical people who calls exponential linear. But then there's this term over here, which is messing things up. And basically what that says is, OK, x star is the optimum for your optimization problem. X true is what the optimum would be if you had an infinite amount of data, right? So basically, this is the statistical accuracy level. It's how well can you do sort of in the best case with this amount of data. And so what's happening there then is that you get this exponential convergence down to where this term takes over, right? And little o means that it's growing less than linearly in this one. So basically, once you're on the same order of magnitude as your statistical error, this term, then this term isn't important. But if you're in the initial phase, which is the phase we sort of mostly care about when we're optimizing a statistical problem, we get this nice exponential convergence. All right, so that's kind of cool. And like I said, this is a subject of current research. You note the 2012 on the paper there, and so I encourage you to take a look at the papers. Was there anything else you wanted to say about this paper?
Pretty good stuff.
Okay, cool. So, whoops. All right, so a bit of administrivia. As those of you who are following the discussion group know, the next homework is out. I hope at least most of you have taken a look at it. It was out last Tuesday, not too long after class. We tried to make it easier than the last one. You'll have to let us know whether we succeeded or not. We hope that we didn't sacrifice interestingness. So our goal is to have one that is just as interesting as homework 1, but not quite as punishingly difficult, let's say. Let's see, we're working on, I shouldn't say we, the TAs, are working hard on grading homework 1. We're hoping to have that back to you sometime next week. The proof that we skipped last lecture, we're going to try and prepare a handout instead of covering it in lecture, because lecture time is pretty, has a high Lagrange multiplier on it. Let's see, scribing. So thank you very much to people who turned in their scribes this week. So we've got most of the scribes for lectures 1 through 6 are up on the website now. And we're hoping to have the rest of lectures 1 through 6 ready by this weekend. Since this is lecture 10, that's 2 weeks ago, we're only a little bit behind the 10-day suggested difference. So that's actually pretty good. That's, only a little bit behind is just fine. One thing I wanted to say is how to handle errata in your scribing. So anybody who's looking through the notes and finds something that they think might be an error, please edit the scribing sign-up document. There's a column for errata or possible errata. And then every so often, people who are the scribes should go and check that column, the entry for their scribe, and update the scribe notes, right? And so we hope this is sort of a low overhead way to collect feedback and make the scribe notes as accurate as possible, because typos in math can be a pain to try and figure out. There are a few days for which we're still missing scribes, 3 lectures, which is not bad out of nearly 30. It's 90%, that's pretty good. One of them is the day right before the midterm, which I guess I'm not too surprised that nobody wants to sign up the last class before the midterm. So if you're an auditor, this is an appeal to you to sign up for that day to scribe, because if you're not taking the midterm, you have a much easier time scribing that day than somebody who is taking the midterm. And then anybody who is signed up as a third scribe for some lecture that has 3 scribes, if you're interested in moving to one of these days, that would be great. Because obviously it's much better to have all of the lectures have at least some coverage. All right. Projects. So we've assigned TA mentors to each one of the projects. So each of you should expect to be contacted by one of the TAs in the next couple of weeks to give you feedback about your project and talk about where it's going. Just so that you have it on your radar, the project milestone report is 10:30, All Hallows Eve. And we'll put up on the website pretty soon what the description is of what you need to hand in, but I just wanted to give you a heads up. So we're shooting for maybe 5 or 6 pages. If you go 6.5, that's not a problem. If you only need 4.5, I'll be surprised. It's due at the beginning of class. What should it have in it? So a literature review, meaning that you've read some papers and understand what they are and how they're relevant to your project. Progress so far, what you've tried, what worked, what didn't work. What you found out about your data set. It turns out that there's noise of this really unpleasant type, so you'll have to figure out a way to work around it. Plots of intermediate results, descriptions of how you're going to set up optimization problems, things that you've tried to solve these optimization problems that you set up, right? It's fine if you have to modify the project goals, right? We expect that is going to happen when you discover cool new things about your project. You can talk about these modifications in your milestone report, but if there's anything that you have any questions about, we encourage you to contact your TA mentor well before the project report. And just for calibration, the milestone report is due approximately halfway through the amount of time that you have to do the project. So you should be well more than halfway through achieving the minimal goals for success that you identified in order to have some chance of, well, having a project that goes beyond those and becomes an excellent project as opposed to merely a minimally successful one. All right? Any questions about the project report? Nobody's thinking about the project report yet, are they? All right, that's what I thought. Okay, so let's see. I've got a new graphics tablet, which hopefully should improve my handwriting, but I'm not quite sure I figured out how to work it yet. So if I do something weird, let me know. All right, so you guys have been studying first-order methods for a whole bunch of lectures now, which is cool. And so you're all ready to go out and apply first-order methods to all of the problems that you encounter in your research. And the first thing that you have to do is calculate a bunch of derivatives, right? Because that's what first order means. It means based on the first derivative. So that's great. You all learned how to calculate derivatives in calculus class. But there's this problem that I like to call matrix calculus pain. So if you're taking a derivative of a function that involves matrices, the sort of standard recipe is you write out all of the matrix multiplications as summations, so you wind up getting this huge multiple summation with a ton of terms. You take the derivative, that winds up introducing even more terms and case statements for whether index I is equal to index j or not. It becomes a big mess. Then at the end, you stare at the output, you try and recognize it as some human readable form so that you can actually figure out what it is and implement it, and you hope that there are no indexing errors, right? So I don't know, many of you are smiling. It looks like you've been there. I know I've been there. So we hope that there's a better way. And that better way is matrix differentials. So what are differentials? So they're basically just a shorthand for working with Taylor expansions. And I'll give that in a little bit more detail, but you can make it precise in a nice way. So let's start with some function f, which is sufficiently nice, let's say continuously differentiable. So the Taylor series is something like, f of y is equal to f of x plus the derivative of f at x times y minus x plus a residual term, right? And this residual term here, it satisfies basically that it's lower order than the difference, right? So the residual of y minus x divided by the size of y minus x goes to 0 as y approaches x with x fixed. Okay? So that's nice. We're going to introduce a little bit of notation for Taylor series to make them more compact. So we'll say that df stands for f of y minus f of x. We'll say that dx stands for y minus x, right? And then we'll write this Taylor thing up here. We'll write it as df is equal to f prime of x dx, right? And then plus this residual term of dx, right? So that's a little bit more compact. We're going to make it even more compact by taking this term and making it implicit. So we don't actually ever even write it, right? Just that there is a residual that behaves according to this rule, right? So we can think of this as just sugar on top of the notation for Taylor expansions. Or you can think of it as overloading the equals operator, right? Meaning that if there's a differential on one side or the other of the equals sign, then you actually mean that they're equal only up to this lower order term. Okay? Now, df and dx here, these are called differentials. That's in contrast to derivatives. And I should emphasize that df and dx don't necessarily stand for small numbers, right? A Taylor approximation makes sense for arbitrarily large increments. It's just more accurate when the increment is small, right? So df and dx, we're not thinking of them as infinitesimals. We're just thinking of them as increments, which we're interested in the small case, but it sort of makes sense for the large case. Okay? So any questions about this notation? All right, so let's make it precise. So we already wrote df and dx for these things here, right? Now, suppose that I can give you a function a which satisfies the following. df is equal to a of x and dx. And I'm going to write a semicolon just because x and dx are going to play a slightly different role, and I want to separate those two arguments, plus this residual, r of dx, right? So suppose that's true. And you have the following. We have a being linear in dx. So that's, it has two arguments. It has to be linear in the second argument for each fixed value of the first argument, right? So we're not saying anything about its behavior in terms of x, just that for each fixed x, it's linear in dx. And so what does that mean? Well, that means that, for example, a of x dx1 plus dx2 is equal to a of x dx1 plus a of x dx2, right? Or a of x and k times dx is equal to k times a of x and dx, right? So it's a linear function. And then the other thing that we need is that r of dx divided by the size of dx has to approach 0 as dx goes to 0, again with x fixed. Okay? Then a of x dx is the differential of f. Okay? So this is the precise definition that goes with the syntactic sugar explanation on the previous slide. Okay? All right. So that's interesting. It doesn't give us much extra power yet. But for a matrix, you can do exactly the same thing, right? So dx is, where x is a matrix, is just the matrix whose entries are dx ij for all I and j, right? And so now if I have a matrix-valued function f, I can write df is equal to some function a of x and dx plus some residual of dx, right? And I want a to be in dx and r of dx. Now this time over the norm of dx has to go to 0 as dx goes to 0, right? And you can actually pick any norm you want here. At least in finite dimensions, they're all equivalent. They introduce the same notion of convergence. But let's say the Euclidean norm just to be concrete, right? So there are some nice examples of this. So suppose we have some function f which goes from Rn to Rm, right? And then we have df is equal to some function j of x dx, right? So here j is going to wind up being a matrix, which is in R n by m, right? And that matrix is called the Jacobian, right? So you've probably seen that in vector calculus, but if not, that's what it's called. Oh, a notation thing. Some books use J transpose instead of J here. 6 of one, half a dozen of the other. The class textbook does it this way, so that's the way I'm going to try and do it. So another example would be if I have a function f which goes from Rn to R, right? Just a real valued function of a vector argument. So then if we have df is equal to g of x dx, right? So, g of x transpose dx, right? No, I'm sorry. Yeah, g of x transpose dx. G of x is called the gradient, right? And then I can take the differential again of g and say that dg is equal to h of x, right, dx. And so that one's called the Hessian, right? And the gradient is going to wind up being a vector in Rn, and the Hessian is going to wind up being a matrix in Rn by n, right? So we can achieve all of the things that we could have achieved with the usual notation, but pretty soon we're going to wind up seeing what the benefit of all of this is, which is that we're going to wind up getting some very nice expressions for matrix differentials, which would be impossible to express nicely using standard notation, right? So if you think about the derivative of a matrix-valued function of a matrix, right? The derivative, you could think of it as a four-mode tensor, right? And there just isn't nice notation for writing out what the elements of those four-mode tensors are. All right, so we'll see some examples of that later. Questions so far? Yeah. Is the h of x is a matrix? That's right. It's an n by n matrix. Yes, typically. So the question is h of x symmetric? And the answer is yes, typically. All right. Okay. So now that we have differentials, we can work with them. So differentials satisfy a lot of the things that you would ordinarily think of as being properties of derivatives, right? So they are linear, meaning that the df plus g is equal to df plus dg, right? And d of kf is equal to k times df, right? And in general, if you have some linear function g, dg of f of x is g of df of x, right? So you just pass differentials through linear functions. And there's a ton of useful linear functions of matrices, right? The linear functions of scalars are pretty simple. It's basically you multiply them by another scalar. But there's a ton of really useful linear functions of matrices. So some examples are the reshape function. So those of you who are MATLAB aficionados have probably run across this one a lot. It's much easier to describe with an example. So if I take the vector of the integers 1 through 24 and reshape it into a 2 by 3 by 4 matrix, what that means is you just, first you go down the columns of the first slice, 1, 2, 3, 4, 5, 6. Then you start filling up the next slice, 7, 8, 9, 10, 11, 12. And you keep doing that through all of the slices of the matrix, right? And you can reshape it into something of arbitrary dimensions as long as you have the right number of elements, right? The number of elements can't change when you reshape something. And now if I take this matrix, which is a 2 by 3 by 4 matrix, and I reshape it into a 4 by 3 by 2 matrix, right? It's the same thing. I just take the elements, and I take the elements going down the columns in the first slice and then the second and so forth, and I put them into the new shape, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then the same thing for the second slice of B. Okay? So reshape is a pretty useful operator. Vec of A, so if you take a matrix A, you can string out all of its elements as a big vector. In MATLAB, that's A of colon. It just strings everything out as a big column vector. You can also write it as reshaping A to be a matrix which is the number of elements of A by 1, right? The trace of A. So the trace is defined to be the sum over I of AII. In other words, it's the sum of all of the elements of the diagonal of A, right? That's a linear function of A, and so you pass the derivative or the differential through it. A transpose, or in general anything that rearranges the elements of A, that's a linear operator, right? So all of these are linear, and we're going to be using that these sorts of facts a lot. Yeah. It means that if you reshape 3 times a matrix, then you get 3 times the reshape of the original matrix, right? Or if you reshape A plus B, it's the same as reshaping A and reshaping B and adding them, right? So linear basically means that you can pull scalar multiplication and addition into and out of it at will. Any other questions? All right. So there's reshape. Okay, so you have a, just like you might expect, there's a chain rule, right? And so in the scalar case, right, what we want is dl of x is equal to f prime of g of x times g prime of x dx, right? That's what that's the chain rule that you know and love or hate from calculus, scalar calculus. But what we want to do is generalize this to matrices. So what we have, just by the definition of the differential, is that df is equal to some function a of g of x and dx, right? And that function is linear in the second argument x. And I'll keep writing this implicit residual term for now because we're going to want to work with it, right? But I'll put it in brackets because, again, we know that we don't have to write it. And then the same thing, we can write dg is equal to, oh, I'm sorry, this should be dg right there, right? And then dg is some function b of x and dx, again, plus a residual s of dx, right? Okay, so let's go ahead and derive the chain rule. Oh, and we know that these residuals, if you divide, for example, r of dg over the norm of dg, right, that's going to go to 0 as dg goes to 0. And similarly for s. So again, for scalars, this would be a would just be f prime of g of x times dx, right? This thing would be a of again dg, a of g of x and dg. Right? So for scalars, it would be that, and then the same thing here. This would just be g prime of x dx. Right? But now we start to see the power of this sort of thing, because for matrices, there's not generally going to be one way that you can write this down, right? There's not going to be a standard form for A or B. And so we're just going to work with these arbitrary functions that are linear in their second argument. All right, so now let's work with this a little bit. So if we just substitute in dg here, right, we have df is equal to a of g of x, and so here we have b of x dx plus s of dx, right, and then plus r of dg, right? And so we can use the linearity of A in its second argument to split this apart. This is A of g of x and b of x dx plus A of g of x and s of dx, right, and then plus r of dg. And I'm going to claim that this part is now a valid residual, meaning that it will go to 0 as dx approaches 0. And then this here is going to be the matrix version of the chain rule, right? And so let's just go ahead and briefly prove that, right? So what we want is for this thing to be a valid residual, what we want is that this divided by the size of dx has to go to 0, right? So what we want is a of g of x, s of dx over norm of dx plus r of dg over the norm of dx. That all has to go to 0 as dx goes to 0. Okay, so can I prove this? Well, so we know that this is linear in its second argument. So what I can do is multiply and divide by the norm of s of dx, right? So this is going to be a of g of x and s of dx over the norm of s of dx, and then the norm of s of dx over the norm of dx, right? So this here, this is bounded because here it's g of x is fixed, and this is a bounded function and a linear. G is linear in its a is linear in its second argument. So a linear function of a bounded set is bounded. This goes to 0, so that means that this whole term goes to 0, right? And then this goes to 0 because, well, it's essentially the same argument. You basically wind up writing r of dg, dg divided by the norm of dg times the norm of dg over the norm of dx, right? And so this goes to 0, and dg over dx, you have to do a little bit more work, but you can show that that stays bounded as well, right? So this is a valid residual, and we get our matrix chain rule. Okay. Any questions? Yeah. That's right. So these functions, this function a here has to be linear in its second parameter. Same with b has to be linear in its second parameter. Yeah. Right. Right. So the general form is a of something semicolon dg, right? But I can write any function which happens to be linear in its second argument. So if you look, for example, at so here, right? This example here, right? This function j of x times dx is linear in the dx argument, right? No matter what j of x is. And so this is a special case, but it's a useful special case. Okay. All right. So given that we have the chain rule, you might expect that we also have a product rule, and in fact that's true. But the product rule is actually again more general than what it was for scalars. So here we have some function L, which is c of f and g. And this function c has to be bilinear. Bilinear means linear in each argument with the other argument fixed, right? So it could be, for example, that L is equal to f times g, where f and g are scalars, vectors, or matrices that are the appropriate sizes to be multiplied together, right? And we know that scalar, vector, vector matrix, matrix, all of these multiplications, they're linear in each argument with the other argument held fixed, right? So already, right, the product rule for scalars was just pretty simple. There's essentially only one bilinear function of two scalars, which is you multiply one by the other. But when you get to matrices, there's a pretty big variety of these bilinear functions. And so the product rule is going to be dl is equal to it's going to be equal to C of df and g of x plus C of f of x and dg, right? And so you can for scalars, right, this is going to wind up being f prime of x. Sorry, let's. Right, so this is, for scalars, this is going to wind up being g times the derivative of f plus f times the derivative of g, right? So that's going to be the scalar case. But for matrices, you can write it this way for any bilinear function c. Okay? And the proof of that is pretty straightforward, but I'm not going to do it here because, well, you've seen enough simple, straightforward proofs to last you probably already for this lecture. But I encourage you to check it if you're interested. And again, there's a ton of different products, right? So if you take the vector cross product, well, the differential of that, it's going to wind up being dA cross B plus A cross dB, right? And because the vector product isn't commutative, it's important that you keep the ordering the same. But other than that, it's pretty much like the scalar cross product. If you have the Hadamard product, so the Hadamard product is known to MATLAB people as dot times. It's the element-wise product. So if you take the ij element of the Hadamard product, it's just aij times bij, right? And the differential of that is going to wind up being dA Hadamard b plus a Hadamard dB, right? The Kronecker product, so again, Kronecker winds up being one of these things that it's easier to show an example than it is to describe it. So if I take this matrix A, right, 1, 2, 3, 4, 5, 6, this matrix B, square matrix whose elements are all 2, Kronecker of AB means that I take each element of A, multiply it by B, and stack the results into a big matrix, right? So 1 times B is 2, 2, 2, 2. 2 times B is 4, 4, 4, 4. 6, 6, 6, 6, 8, 8, 8, 8, right, and so forth. And if you do it the other way around, right, twice B is 2, 4, 6, 8, 10, 12. And there are 4 copies of that because A has 4 elements in it. Okay? So that's the Kronecker product. And you're probably not surprised to learn that if you have the differential of the Kronecker product, it's going to be dA times B plus A times dB, right? And the Frobenius product, so I should say the Kronecker product, it's a generalization of the outer product of vectors. The Frobenius product, it's a generalization of the inner product on vectors. And this is equal to sum over ij of aij times bij. And I'm not even going to write the product rule because I'm sure you can guess what it is. It's exactly the same as all of these other forms. And in fact, if I tell you that there's some weird type of bilinear form called the Khatri-Rao product, which I hadn't heard of until pretty recently, and so I'm guessing that a lot of you haven't heard of. Yeah? But if I tell you it's a bilinear form, you're going to be able to tell me that, in fact, the differential is dA times B plus A times dB, right? In case you're interested, the Khatri-Rao product, it's like a blockwise Kronecker product. So you divide A and B each into the same number of blocks and do Kronecker products within each block. Turns out to be useful for some reasons. which we're not going to go into here. All right, and all of these products are associative. They're bilinear. They're not generally commutative, except for the scalar ones and the Hadamard product. This one is commutative. Okay. All right, so now you have not just one product rule, right? Just wait, there's more, right? You can have as many product rules as you can think of bilinear forms, no extra charge. Okay, just a few few rules for working with a Hadamard product, because it's gonna wind up being useful. So if you have the Hadamard product of two vectors, you can write it as the product of a diagonal matrix with A on its diagonal with B. That's the ordinary matrix vector product. It's also equal to diagonal B times A, right, because it's commutative, so you can do it either way. If you have the product of two diagonal matrices, right, it's a diagonal matrix with the Hadamard product on the diagonal, right? So the trace of a product of diagonal matrices, anybody want to take a guess what that is? Yes, so somebody said A transpose B, right? So it's the dot product between A and B, right? The trace is the sum of the diagonal elements, so it's the sum of the products of corresponding elements in A and B, which is the dot product. And then this one's kind of interesting, right? So I can take the trace of diag of B and write that as the trace of the identity times B, right? Because I can put in a spare identity, but I'm going to write the identity slightly unusual way. It's the diagonal matrix with the ones vector along its diagonal, right? And so that's now 1 transpose B, otherwise known as the sum of the elements of B. All right. Okay, so that's matrix differentials, the whirlwind tour. We'll do a couple of examples just to sort of show you how to work with these things. So if we take a look at yes, that's right. Thank you. All right, so suppose that we have a, this is a matrix valued function, right? Y minus xw transpose y minus xw, and we want its differential with respect to a matrix W. So we can just expand out and say that this is the differential of y transpose y minus y transpose xw minus w transpose x transpose y plus w transpose x transpose xw, right? And then the derivative of a constant is 0, right? Then this is minus y transpose x dw, right? Because we just go through a linear function, minus dw transpose x transpose y, plus, and now we have to use the product rule because there are two terms that depend on w. So we can have dw transpose x dw plus w transpose x dw, right? So this is a nice simple expression for the differential, and if you were going to write it out during or using the ordinary notation, you'd have to figure out some notation to have a 4-dimensional tensor, right? Because it's got 2 matrix arguments in it. Or you'd have to use string W out into a vector and do the indexing pain in order to figure out how to write it using ordinary notation. Okay. This example makes sense to everybody? Yes? Cool. So couple more examples. Suppose that I have a matrix X, right? And I say that my function that I care about is the ij element of X squared over 2, right? So you can sort of just eyeball this one and figure out that DL is a matrix which is mostly zeros, right? And then in the ij element, we have xij, right? 0, 0, all of that, right? And then this matrix, Hadamard product with dx, right? In other words, L only depends on the ij element, so the derivative of L is going to wind up being 0 everywhere except in the ij element, and in the ij element, it's going to wind up being xij times dxij, right? Or if we have something a little bit more complicated, like X transpose X, the ij element squared over 2, right? Well, we can use the chain rule, right? So this is going to, for the same reason, it will be this matrix here, right, with a bunch of zeros, and then X transpose X, the ij element, right, and then a whole bunch more zeros. Hadamard product with the differential of X transpose X, right? So that's just using this, what we already calculated, with the chain rule for the Hadamard product. And so I'll write that as a matrix M, and then Hadamard product with the differential of X transpose X, which by the product rule is dx transpose times X plus X transpose times dx. Right? And again, this one would have been pretty difficult to write in the ordinary way. All right? Everybody think they can do these? I'll take silence as assent. All right. So the goal now is going to be to give you a real interesting example of how to derive some actual algorithm using using this sort of notation. I'm going to use another little bag of tricks. So I have 3 more slides of bags of tricks, and then we'll go into the real example. So let's try and get those the bags of tricks through, and then maybe we'll take a break. So I already defined that the trace of a matrix is the sum over all I of its diagonal elements. Trace is linear, so it's going to wind up that the differential is it just passes through like that. If we have a scalar x, right? So I'll just write that is a scalar, S-C-A-L-A-R. Well, that's just x, right? The trace of a 1-by-1 matrix, it's the sum of all 1 elements on its diagonal. The trace of X transpose is the same as the trace of X, because when we go down the diagonal, while transposing it doesn't change what the diagonal elements are. Right? So if you remember the Frobenius product, A colon B was the sum over all I and j of Aij, Bij, right? Well, I'm going to claim that that's equal to the trace of A transpose B. Okay. Can I prove that? Hopefully. So A transpose B, the ij element, is equal to, well, the sum over all k of Aik times Bjk, k, right? That's just the definition of matrix multiplication and transpose. And then if I sum over all I, A transpose B I, this is equal to the sum over I, sum over k, right, of A I k, B I k, right? And so that's actually exactly the definition that I gave right here, right? I actually wrote the transpose backwards, right? So you're right. This should be sum over k, A k I, B j I, right? Instead of that, and then instead of this, sum over I, sum over k, A k I, B k I. Thank you. No, because I'm taking all of the diagonal elements, so where? Oh, here. B k j. Thank you. Speaking of indexing pain, right? This is why we're doing the matrix differentials, is so that I don't have to make mistakes like this in front of everybody. Okay? All right, so trace has some nice properties. In addition to being linear, we have trace rotation. So if we have so A times B is a square matrix in order to be able to take its trace. And the trace of A times B is equal to the trace of B times A, right? So this is kind of interesting, right? Because suppose A is an M by N matrix and B is an N by K matrix, right? I guess it has to be an N by M matrix, right? So M times N multiplied by N by M, right? That's an M by M matrix. If you multiply them in the other order, you'll get an N by N matrix, but the trace of those two things is the same. I'm not going to prove that, but it's a pretty useful fact. You can go home and verify it if you like. But you may see it also written in the following form. Trace of ABC is equal to the trace of CAB is equal to the trace of BCA, right? So this is why it's called trace rotation, right? You can just shift all of the matrices one place around the cycle, right? And the equality will still hold. And now for the second one, we can actually have B be N by K, and size of C has to be K by M, right? So the whole thing has to be square, but depending on what order you multiply it in, it could be K by K, M by M, or N by N, right? So that's kind of a useful identity. And then there's just tables of derivatives. You can't get away from those. But some of the common ones that we'll be using is that the differential of the inverse of a matrix, you can write it as x inverse dx x inverse. Kind of cool. The differential of the determinant of a matrix, well, that's going to be the determinant of the matrix times the trace of x inverse dx. Also not obvious, but true. Somebody's probably proved them somewhere. Almost certainly. This one is going to wind up being quite useful for reasons that may not be clear. If you take the determinant of a matrix, so that could be positive or negative. So let's take the absolute value of the determinant of the matrix, and then take the log of that. Not clear why you'd want that, but it'll come up surprisingly often, actually. The differential of that is just trace of x inverse dx. Okay? And you can sort of think of that as, well, you do sort of 1 over the determinant times the differential of the determinant, and so they cancel, right? And then you have to handle the sign in the appropriate way, but it still works out. Okay? So, and there's a ton more, right? There's, you know, as many, you can get identities to fill books with, if you like. Okay, so let's take a brief break, and then when we come back, we'll try and do a real example with this.
Is this still on? Oh, I think on one of your slides you might have written a DF or you might have meant a DL.
Oh, okay.
You did the chain rule. I just wanted to
Do you want
put
to?
that out in case when you post it might be.
Yeah. Okay. So let's. Do you see the slide here?
Yeah, it's the one where you derive the chain rule. Like here, for example, you're wanting that to say DL at the end, right? Because this is what you're
Oh, yeah.
deriving. And here too, I think. This is kind of like DF evaluated at G.
Mm-hmm.
I don't know what the notation you'd want for that.
Yeah, you're right. Okay, I definitely have to. I'll fix that notation before I post
how
that.
you, like DF evaluated at G as opposed to at X. Do you know what I mean? And that should
Yeah,
probably
this-
be DL.
Well, so this is this. The only thing is that this should be DL.
Yeah. Yeah, I guess I could write. I mean, you can maybe get rid of the X there, but I'm not sure if that makes any more sense.
No,
But
I mean you're evaluating. You're evaluating. Right. You could just.
I could put anything in here, right? As
Right.
a dummy variable. So I suppose.
Right. Yeah, I think it's probably least confusing with the X there, but I could be convinced another way.
What's that tablet, by the way? I didn't see that. This is new.
Yeah. So this is
You still can't see what you're.
no, but so the difference. I don't know if you can see, but to me, my handwriting looks a lot
I
better.
think it looks clear. Yeah.
Basically, this has a bigger digitizing area and much higher digitizing resolution.
Yeah.
So it has something like 16 times as many pixels.
Okay.
I was noticing actual jaggies in my handwriting on some of the earlier
Well, I
slides.
can see that you're underlining something very precisely. I thought maybe you actually had the screen there, but
No. I still have. Yeah, it's still just practice. All right, so let's start back again. Just wanted to point out that Ryan pointed out a typo on page 10. I wrote DF where I meant to write DL. So I just fixed that. Yeah, now let's go back to our real example. Whoops. So the first real example is linear regression, right? So we have a bunch of training examples, xi, comma, yi, for I equals 1 to n, right? So the input feature vectors are xi, which are vectors in Rn, right? The target vectors are yi, which are vectors in Rk, right? Let's actually call this, I think in my notes I called it Rd, so let's actually make it Rd so that I don't switch back and forth. And then we have a weight matrix, capital W, which is going to be a function from x to y, which means it's going to be a matrix in R k by d, right? And we want to minimize the sum of squared errors over all training examples, which is the sum over I of the difference between yi and w times xi, the two norms squared. Or we can write this, right? So this is the sort of standard linear regression objective. We can write it as a matrix, the matrix Y minus the matrix W times X, where here we have something that looks like this, right? We have the matrix Y, which is K by N, and that has to equal W times X, right? So let's say it's like this, W. There are d-dimensional feature vectors and k-dimensional output vectors, and then X is a matrix that looks like this, should be the same length as Y, right? And is N by D, right? So this is the, and then, for example, if we look here, right, this is the ith column of X and the ith column of Y are together the ith training example. Okay? So we can take Y minus WX, and we want to sum all of its squared elements. That's the Frobenius norm, right? And that's basically what we want to minimize. Okay? So we have L is Y minus WX Frobenius norm squared. So another way to write the Frobenius norm is the Hadamard product of the matrix with itself. Right? Sorry, not the Hadamard product, the Frobenius product. Right? The sum of products of corresponding elements. Right? And this is equal to the trace of Y minus XW transpose Y minus XW. Remember, we proved that about the Frobenius product. And so we can write that out again, expand that as Y transpose Y minus Y transpose XW minus W transpose X transpose Y plus W transpose X transpose XW, right? So if we want to take the differential, then this is equal to minus the trace of Y transpose X dW, right? Actually, we'll plus dW transpose X transpose Y plus the trace of W transpose X transpose XW, right? Just using linearity at this point. Now, the interesting thing is that the trace of a matrix is the trace of its transpose. So I can just take the transpose of this term, which is Y transpose, I should say D that. And then this should be Y transpose X dW, right? And so here, this is just, this term is the same as this term, and so we can sum it. And this is equal to minus 2 trace of Y transpose X dW plus, and now this term here, right, I write it out as dW transpose, the trace of dW transpose X transpose XW plus W transpose X transpose X dW, right? And that's the same product rule that we've been using. And we can do the exact same trick. This and this are transposes of each other. And so this is plus twice the trace of X transpose X. Sorry, let's plus the trace of W transpose X transpose X dW, right? And so now I've computed, this is a nice simple form of the differential, right? And if I want to solve it, I can set the derivative to 0. The derivative is just the coefficient of dW, right? So I can say that, well, these 2's cancel, I'll just ignore them. We have Y transpose X is equal to W transpose X, right? And now I can multiply both sides by the inverse of X transpose X, get Y transpose X, X transpose X inverse is equal to W transpose. And I can take the transpose of that if I want, but that's basically the normal equations. Yeah? So if the only way for the trace to be 0 for all possible directions that you could move W is for that coefficient to actually be 0. That's a good question. So the question was, does the trace being 0 necessarily mean that the coefficient of dW has to be 0? And the answer is the only way for it to be true for every possible dW, for every direction you could move W in, is for the coefficient of dW to be 0. Yeah? Because I made a mistake, I believe. Oops. So did I consistently make that mistake throughout? It looks like I did. So you can do linear regression the other way if you prefer. So that just means that you transpose the definitions of X and Y on the previous slide. It's easier than crossing out all of the rest of the slide. Right. So, right. So that's a good point. Any other questions? Yeah. If two traces are the same, right. Right. So in general, two matrices can be different and have the same trace. But what I want is for them to be the same no matter what dW is. And for that to be the case, the two matrices have to be the same. All right? So this is nice, right? Because we just derived linear regression in one slide with no use of I and J in the entire slide, right? So this is to me a much faster way to derive linear regression than sort of the standard way where you have to take the derivative component by component. But this isn't even the best example of making it easier. It's just linear regression isn't too hard to derive anyway, but we make it just a few lines here. Okay. So I don't know if we'll have time to do. Actually, we will have time to do this. Go ahead. So I just took the transpose of X and so if you look here, here are the definitions of X, Y, and W. If you take the transpose of this equation, right, Y transpose is equal to X transpose W transpose, and then just rename everything to be its transpose. I apologize about that, but yeah, it would be more boring for you guys to watch me rewrite the entire slide. All right, so sometimes it's useful to go back and forth between the matrix differential way of writing things and the ordinary derivative way of writing things. So again, this is not always possible. You remember our example where we had the differential of x transpose x was dx transpose x plus x transpose dx. And if you try and write this out as in matrix notation, it's going to be, it's possible, but it's not something you actually really want to do, right? So there's 6 common cases where you can go back and forth easily, and these are called identification theorems. The simplest one is that if you have a scalar function f of a scalar input x, if you see df equals a dx, then a here is the ordinary derivative, right? A becomes df dx. Okay? But there's 5 other cases. I don't know what to necessarily say about any of them, except that, let's see, so we used this one already, right? The derivative of a matrix with respect to the derivative of a scalar function with respect to a matrix input. You can write that as trace of A transpose times dx. And here A transpose is the derivative, and that's what you want to set to 0, right, if you're minimizing or maximizing something. That's what we used in the previous slide. If you have this case here, right, this is the gradient. A here is the gradient vector. And capital A here, this is the Jacobian matrix. We did those before. These are the sort of most common matrix cases. Right, so I guess I'll label those. This is the gradient, and this one is the Hessian, right? This one here, so if we have a vector function with a scalar input, you can think of that as a parametric curve in Rn. And here, the vector A is the tangent to the curve, otherwise known as the velocity vector, right? And then I don't know of a name for this one. You can think of it as a matrix velocity or something like that, right? It's a one parameter family of matrices, and you can take a tangent matrix to it. I do, in fact. Thank you. Thank you very much. Okay, and then these ones here, right? These empty cells, these are the places where there's no standard way to go back and forth between the notations. Okay. All right, so I guess the thing that I have next is a real example. It's going to take us longer than the linear regression example. So I don't think we'll finish it today, but we'll at least get started with it. Okay, so suppose that I have some training examples xi, which are in Rd, for I equals 1 to n. And I think about some transformation yi is g of w times xi. So w is a parameter, right? So it's a parameter which is a d by d matrix, right? And g is just some component y, is some scalar function, and it's applied component wise. Okay? So here's an example of what I want to happen, what I want to design an optimization objective for. I have these xi, they're scattered in 2 dimensions, and you can see that there's sort of this direction going that way, and there's sort of this direction going this way, right? And so there's sort of 2 things that are going on, right? There's sort of heavy tails in 2 different directions. If I were to apply the correct matrix W, then maybe I could resolve the two axes, right, so that they were horizontal and vertical. That was surprisingly non-horizontal. There we go. And the way we're going to do it is by saying, okay, g is going to be, let's say, the sigmoid function, which it takes an arbitrary real number and puts it between 0 and 1. And so if I apply the sigmoid to each component, I'll get this cloud of points. And if I've disentangled these two axes, then it's going to be the case that I can make the two coordinates here statistically independent, right? Meaning that I have essentially, for example, one independent distribution would be the uniform distribution over the unit cube, right? And so what I want is, well, independent components, which is why it's called independent components analysis, right? Hence the name. So that's my goal. And the question is how I'm going to achieve that. So this is just copied from the previous slide. Y is g of wxi. So we're going to be able to write dyi as some Jacobian matrix, j of xi and w times, actually I just want this to be an ordinary function. This isn't a differential. J of xi comma w times dxi. Okay? And I'll just shorthand that as ji dxi, okay? And ji is the Jacobian matrix at the ith example. And the method that I'm going to do is to try and get as uniform a distribution as possible for the yi's, is to try and maximize an estimate of the entropy of yi, right? So yi is a random variable. I can compute its entropy, and I can try and make it as large as possible. And that's going to make it as close to a uniform distribution over the hypercube as possible, because the uniform distribution is the distribution with maximum entropy over the hypercube. Yeah? The objective is to find W. Right. So right here, I'm finding the differential with respect to xi. And you'll see why in a few minutes. But that's a very good question. We could ask for the differential with respect to xi or with respect to w. Right here, I want the Jacobian matrix with respect to x. Okay. So we can get an empirical estimate of the entropy, right? The entropy is the expected value, or is the integral of minus p of y log p of y, right? So I can get an estimate of that by taking a sample of y and summing minus log p of yi, right? And so what is p of yi? Well, I can compute that from ordinary calculus. It's going to wind up being p of xi divided by the absolute value of the determinant of the Jacobian of xi. Okay? This is a standard formula for transformations in statistics and calculus. Basically, what it is. So Ji is it's a linear transformation. It takes the unit cube in x space, and you multiply by this linear transformation, and the image of the unit cube will be some parallelepiped in y space, right? And the volume of that parallelepiped is the absolute value of the determinant of J, right? You can sort of think of it as J tells you, each column of J tells you where you map one of the unit vectors. And so if you map this guy to some squeezed parallelepiped, the columns of J are going to wind up being those vectors. And so the determinant of that matrix is going to wind up being proportional, essentially the sides of the matrix, right? The sides of this parallelepiped, you take the product of them to get the area, and that's what the determinant is. Okay, so the intuition is if it's squeezed into a small volume, the probability density is going to go up, right? You divide by the determinant, which is going to be small, meaning the probability density will go up because lots of x's are squeezed into a small volume in y space. If the determinant is huge, that takes the same number of x's and spreads them out over a big volume, and so the probability density goes down, right? So this is the area transformation formula. Okay, so that means then that what we want to do is to maximize over W the sum over I of the negative log of this thing, right, which is the log of the absolute value of the determinant of j of xi minus the log of p of xi, right? I'll put some parentheses here and here, right? Now, interestingly, we don't know p of xi, right? Xi was just our random sample from some unknown distribution, but it doesn't have any w's in it, so we can just ignore it. Okay, so that's a good thing. So our goal then is going to wind up to maximize over w the sum over I of the log of the absolute value of the determinant of j of xi. And j of, sorry, this will be j of xi and w as well, right? So does the setup make sense? This is, we're going to try and maximize an empirical estimate of the entropy of y, where y is a transformation of x with parameters w, and we can do it by maximizing this formula. All right, commit the formula to memory, and we'll start taking differentials next time around.